Hello, everybody. I'm Miao. I'm very happy to present our work on joint code and belief propagation decoder design for quantum LDPC codes. We have presented this at ISIT 2024, and this is a joint work with my colleagues. And here you can see we have a camel. You cannot yet find why we have a camel here, but you will see it along the presentation. I will start with some background. So quantum error correcting codes, they are crucial for realizing reliable quantum computers. And quantum LDPC codes are promising candidates for this task because they have many advantages. And then we use belief propagation for classical LDPC codes, and usually they are very suited and give us really good performance. And then in principle, we know that if we just use a quaternary belief propagation and modify it slightly without violating this bitwise MAP rule, then we can actually decode quantum LDPC code in this way. And the crucial thing is we want to map the 4 different kinds of poly errors into the 4 elements in the GF4 field. And then it seems that the problem is solved, that we have quantum LDPC codes, then we can decode them. And then we found there's a big problem is that usually if we directly decode quantum LDPC codes with BP, we get very bad performance. If we look at classical ones, then they are completely not comparable. So why is this the case? We can look at this example here, which is a small toric code. And we see that this is uncoded, and this is the minimal weight perfect matching decoder, which is the near optimal decoder for a toric code over the depolarizing channel. Then we see that if we use BP decoding, it's so much worse than the other decoder, and it's almost not giving any advantage compared to the uncoded case. And why is this happening? We want to look at this problem. So then we realize the first thing is that we cannot avoid short cycles of length 4 in the telegraph. And if we know classical LDPC code, then you know that short cycle of length 4, they are very harmful. They cause many trapping sets, and 4 cycles also form further 6 cycles and so on. And then we want to see why is this unavoidable. We can look at the CSS type QLDPC codes, which is the focus of this work because they are mostly widely used and they give simple implementation of the quantum circuits. So they are formed this way. We have 2 binary matrices, HX and HZ. And if we put omega and omega bar in the front, so this is a scalar product, then we get a quaternary paracheck matrix of the QLDPC codes. And we know that as long as the product of HX with HZ transpose is 0 modulo 2, then we have a valid stabilizer code. Then we take a closer look. We see that this means that every row of HX must have an even number of overlapping ones with every row of HZ because they are binary matrices. And then we look at this further. We see that if we want to have an even number of overlapping ones, then we can either have no cycle, so all the ones are disjoint, or we have to have 4 cycles. Then for the first case, we know that if we have a code with this tree-like telegraph, so no cycle, then we will have a very bad minimum distance. So this will not give us good code. Then we have to live with the second case with 4 cycles. Okay, then we have some existing solutions which tries to address this issue. The first one, we can decode them. Decode the quantum LDPC codes by decoding X and Z errors separately by looking at HX and HZ as 2 separate binary matrices. Then we can just use binary belief propagation decoding, and we can avoid 4 cycles inside HX and HZ respectively. This is good, and for this individual decoding is you can get pretty good. The problem is that overall performance, if we consider a depolarizing channel where the 4 types of Pauli errors, they occur independently with a certain probability, then the binary decoding is suboptimal because it's estimating X and Z errors separately. Then for the Y errors, it's a combination of X and Z error. Then the correlation between the different errors are not considered. So this is suboptimal, even if the binary decoding can be optimal. So we don't want to live with this solution. Then we want to look, can we directly improve the quaternary decoding? Then there are many works that have been done to improve this decoding in this case. For example, there's many references here and even a lot more. And the problem is that for one thing, we cannot guarantee to improve the decoding performance under the presence of 4 cycles, because we can fine-tune the decoder, but we don't really know how much we are from the optimum. Also, we don't really know what is the optimum for quantum code decoding so far. And then the complexity also goes up, and the latency is also increasing for most of the works here, and which is very bad for quantum error correction, where we have to continuously decode because the quantum qubits, they are constantly under the presence, under the influence of noise. So we have to decode with very low latency, so which makes these methods not so desirable. Okay, then we want to ask this question: if we cannot really improve when we just arbitrarily construct codes, then they have harmful structures for decoding by just working on the decoding side. Can we go to the beginning and consider the code construction and construct some codes with 4 cycles, but the 4 cycles are not harmful for decoding, or we know an optimal way to remove them? And the answer is yes, and is with Camel that we have proposed in this work. Okay, we still haven't explained what is Camel, but very shortly you will see. Then we want to introduce the idea of Camel, which is a joint code and decoder design as the title of the paper. So we first look at a part of the code design. So we repeat that the key step in designing quantum LDPC codes is to find 2 matrices, binary matrices, such that their product is 0. So now we have formally defined them to be over F2. So this is just, so we omit this modular 2 as we did earlier. And then we have an idea is that we don't directly construct this matrix, which don't really allow us to optimize the tangraph's structure. We want to take a detour and construct H1 and H2, which is just 1 column less than HX and HZ. Then we let them to fulfill that H1, H2, the product is all 1 matrix. So this means it's 1 everywhere. It's not identity, and it's all 1 matrix. Okay, and then we let HX to be H1 by appending all 1 column to the right. So just 1 column. Then HZ the similar way. Then we can verify that HX times HZ transpose is this here. And this equals to H1, H2 transpose plus this all 1 matrix, which is all 0 matrix. Then we go back to this the criteria for designing QLDPC codes, and it's a valid stabilizer code. And the advantage of doing so is that if we let 2 matrices, their product to be 1, that means that we essentially have just 1 overlapping between the rows. Then this ensures no 4 cycle in the tanagraph associated with S prime. So S prime is constructed similarly as the S we did before, just with H1, H2. Okay, and then we also realized that this is the starting point of some good classical LDPC code construction method. For example, this one where they use finite geometry, because if we start with a parity check matrix with no 4 cycles, then they can be used as a good starting point. You can later modify this parity check matrix to get good LDPC codes. So there are many different constructions which gives us this matrix in the literature of classical LDPC codes. So I will not go into detail of how do we construct finite geometry codes, but I will give you some results later. So next we want to look at decoding part of Camel, which is ensemble decoding. In the ensemble decoding, we want to take 4 parallel BP. So we have said we want to only use BD propagation decoding because it's very nice. In the quantum case, it's graph local, and we can have very low latency if we implement them properly, and it's not complex, and the latency is scaling with linearly with the number of iterations and with the number of iterations. Okay, then the idea is that if we use parallel Billy propagation, then the latency is the same as the single Billy propagation because it's parallel. And then we can feed a hard guess of the last bit that is corresponding to this all one column that we have appended by taking the hard guesses. So we have 4 possible values, 0, 1, omega, omega bar, which correspond to the Pauli errors identity, X, Y, and Z. And then we can decode with this hard guess using a BD propagation decoder. And then we know that if we look at the decoding rule, that we quickly realize that if we do this, it is the same as removing this last column in the decoding. So we're essentially decoding over the tanagraph of S prime, which we have constructed to be a good tanagraph for BP decoding. And then we can have 4 estimations from the BP decoding. Not all of them will be valid error patterns. Some will declare failure, but it's okay. Then we can take the error of lowest weight to be our final estimation. So you see that by this, we have actually just partitioned the whole error, possible error patterns into 4 groups by their value of the last bit. Then together, we want to call the cycle assembly and mitigating ensemble decoding, which is shortly denoted as CAMEL. Okay, now this is the principle of CAMEL. So we want to also construct some new codes for quantum LDPC codes. So we want to look at quasi-cyclic codes because they are very beneficial in many cases. For example, encoding, for example, storing the parity check matrix, and also they are more structured and easier for the implementation. So what is the quasi-cyclic code? Quasi-cyclic code is obtained from some base matrices. For example, here we define the lifting size P, which we explain later, P is 3, and the base matrix has to take value from 0 to P minus 1. And then, for example, we just take 0, 1, 2, and we do a lifting, which is a process by replacing the element in this non-binary base matrix by binary cyclic permutation matrices. And what is a CPM? CPM is obtained by cyclically right-shifting the rows of the identity matrix by X positions. For example, here from 0, 1, 2, we denote this lifted matrix as SIC H, then we say this is a binary H, then you can see identity shifted by 1 and shifted by 2. Then we have a quasi-cyclic code. And we have some very nice property of the CPMs. That is, they are actually isomorphic to the integer group modular P, so with addition. Then we see that the matrix product is mapped to the addition of the elements in ZP in this additive group. And then the transpose becomes taking the additive inverse, and then we have Ix, Iy transpose is essentially just Ix minus y. And so this is our preliminary for constructing the codes. Now we want to repeat that we want to obtain two binary matrices whose product is 1. And by doing so, we want to consider one row of H1. So this is the base matrix, and one row of B of H2, and they will be lifted to a row of CPMs. And then we also just define a difference vector as B. Then we have conditions for getting camel code is the assembling condition, where we have the lifted binary matrices, their product needs to be 1. And what is the product of these two that we can calculate? This is essentially summing up IAI times IBI. So AI and BI are elements of A and B. And then this is using the property of the CPMs. This is IAI minus BI. Then this is IDI, and summed up for all the I's. Then we realize that this addition is the addition of different cyclic permutation matrices, and we know that CPMs, they are either completely identical or disjoint. So if we want to have all one matrix as a summation of different CPMs, then we just have to have DI covers all the possible values from 0 to p minus 1. So it means that D contains all elements of FP and odd number of times. Okay, then we also have a girth condition where we want to have a tanagraph of S prime to have girth at least 6. Then this we can just use the conclusion from the work by Hagiwara. And that means that D has to contain no elements of FP more than once. And this together, we can summarize that the difference vector between any two rows of H1 and H2, the base matrices, need to be permutations of from 0 to p minus 1. And then we give this construction that in the paper is constructed in this way, such that we take sigma, which are the generator of the multiplicative group of FP. And then if we arrange them this way, you can check just if you sit down with the paper for a couple of minutes, then you will see that you can verify that the difference between any two rows is a permutation vector. Then we can do appending one column, and then we can partition this lifted binary matrix into HX and HZ. Then we will have a valid quasi-cyclic quantum LDPC code. So this is the performance from the constructed code. We have the parameters listed here, you can see. And then we have also calculate the minimal distance using probabilistic searching. Then the minimal distance is roughly square root of the block length and slightly larger. And then we plot the frame error rate or logical error rate over a depolarizing channel. And we want to stress that we only want to use 15 iterations of flooding BP decoding. And this is to achieve a lower latency. And for the smaller codes here, you can even use only 10 or 7 iterations. And then we want to also have some comparison with the literature. For example, we take the curve from the paper by Ruffel, and we look at this 416 hypergraph product code, which is decoded with a high complexity BD propagation concatenated with ordered statistic decoding processor post-processing. And then we see that the parameter is comparable to Q5 with even lower rate, but you can see that our Q5 code is much better than R1 because hypergraph product codes are not so good with BD propagation decoding. And then we also want to show the codes over finite geometry that we mentioned earlier from classical literature. And here we also list the parameters. Their minimum distance are also roughly square root of the block length. And we want to have a comparison with, for example, this half rate bicycle code, which is comparable to E5, but this R2 will be using a modified non-binary decoder with enhanced feedback post-processing. So we took this curve from the paper by Babar, and you can see that our E5 only use a 15 iterations of Latin BP, and we are still better than this bicycle code. So we want to also give you some insights on why is Camel behaving so well. We can look at one example code is one of the EG code that we constructed. So first of all, we want to compare BP2 and BP4 without any modification. We directly decode without using the ensemble decoder. Then we see that BP4 is slightly better, but then they converge around this floor area, and we can use BP2 OSD to further improve BP2 a little bit, so binary BP a little bit, but not so much, because we see that the BP2 has really bad estimation for the OSD. Then the OSD have to suffer this very bad input, and the improvement is very limited, even though we have used the highest order that we can afford to calculate. And then we want to also look at some ideal case, which is we have this one column that we appended, which is causing all the 4 cycles. And we think let's have some gene-aided version of the decoding, that is, would just feed the last bit to the correct value. So basically, we don't need to consider this one last column. Then we can decode optimally for the rest of the bits. Then we get this 2 dashed curve for BP4 and BP2. BP4 is still quite a bit better because it uses the correlation of the errors. Then we want to finally assess the performance of Camel, which is using ensemble decoding, and we can see that it's very close to the gene-aided version. The reason is that when we guess the last bit, if we guess it wrongly, then usually the decoder will not converge, or will converge to a very high error estimation is degenerate, but we will always take a lower weight estimation, because the decoder is fed a very bad wrongly guessed input with infinite reliability, which will just causing the decoder to not work properly. That's why we almost always succeed just as the gene-aided version. Okay, so this would be the content of my presentation. We want to emphasize that we have constructed the first family of quantum LDPC codes which are naturally suited for BP decoding. By carefully assemble all the short cycles on one specific VN, then we can nicely remove them during the decoding. Then we achieve good performance. Thank you very much for your attention. If you have questions or want to discuss, feel free to contact us or comment below.